Welcome back, everybody. This is the second FRQ question for the AP Unit 3, which is Cellular Energetics, which again corresponds to our chapters 8, 9, and 10, everything from enzymes and cellular energetics through respiration to photosynthesis. So let's take a look at question 2, which actually looks to me like an enzyme question. So enolase, so they tell you that enolase is an enzyme, notice the ACE, is an enzyme that catalyzes one reaction in glycolysis in all organisms that carry out this process. The amino acid sequence of enolase is similar but not identical in the organisms. Researchers purified enolase from Saccharomyces cerevisiae, a single-celled eukaryotic yeast that grows best at 37 Celsius. And from Chloroflexus aurantiacus, a bacterium that grows best at a much higher temperature of 55 degrees Celsius. The researchers compared the activity of purified enolase from the two organisms by measuring the rate of reaction in the presence of varying concentrations of substrate and a constant amount of each enzyme at both 37 Celsius and 55 Celsius. So depending on the organism, the optimal pH for enolase to catalyze its reaction is between 6.5 and 8.0. Describe how a pH below or above this range is likely to affect enolase and its catalytic ability. Okay, so nothing directly about this because it's talking about temperature. This is pH, but as you guys know, it can definitely affect the activity of an enzyme because again, each enzyme has an optimal range of conditions, which can include things like temperature and pH. And so you guys did a lab on this, where you guys, you had that yeast enzyme, and you guys saw how it catalyzed the decomposition of hydrogen peroxide in different conditions. Some of you guys did temperature or pH. But just like when you were analyzing that data, you realize that when an enzyme is outside of that optimal range, activity goes down because activity decreases because the protein begins to denature, right? Enzyme begins to denature. Either because it's somehow interfering with the interactions of the R groups in the protein, which then will cause the enzyme to begin to unfold or change its shape enough that it can no longer catalyze the reaction that it's there to catalyze. So let's look at part B. So identify the appropriate negative control that the researchers most likely used when measuring the reaction rate in the presence of each organism's enolase. Okay, well, the key here is, negative control, right? So we've used negative controls in many of the experiments that we've done over the years, or over the year. So the negative control just means that something isn't there, right? So if your experimental groups are going to be enolase from the bacteria and enolase from the yeast, your negative control is going to be no enolase, right? No enolase. You're just going to have the substrates. Because varying concentrations of substrate and a constant amount of each enzyme. So you just take the enzyme out, right? You just have the substrate there at 37 and 55. Just to kind of prove or to demonstrate that it is indeed the enzyme that's responsible for the change in reaction rate. And then at the end, researchers predict that for any particular concentration of substrate, the enolase catalyzed reaction is more rapid at 55 than at 37. Well, because the range, right? Because the optimal range of that enzyme is around 55 degrees Celsius. Because that's the environment in which it lives. And if it's talking about provide reasoning to justify, so natural selection would select for an enzyme that is optimal for the environment. And if your environment is 55 degrees Celsius, which is extremely hot, but for that environment, it would select for those organisms that had an enzyme that was active at 55 degrees Celsius. It's like when we were talking about Taq polymerase, that their DNA polymerase is active at 80 degrees Celsius or whatever, because they live in those hot springs up in Yellowstone. Okay, so let's see what they were looking for. pH above or below this range, analyze to denature, change the shape, less efficient, unable to catalyze the reaction. Okay, so check there. The response indicates that the appropriate negative control is to measure the reactive reaction rate without any enzyme present, right? Again, negative control, nothing there. And then more stable functional protein structure at the higher temperature of 55 Celsius. Enzyme is from an organism that's adapted to growth at 55C. Okay, so again, this one fairly straightforward, especially compared to the first FRQ question. Okay, thank you very much, and I'll be back with the Unit 4, 5, and 6 progress checks. I'll probably get them uploaded tomorrow. Okay, thanks a lot, guys. Have a good one. Bye.